All right, I'm going to keep going on part one of the static electricity notes. Very quickly, there's this table in the middle of the first part of the page, and basically it just sums up what we've already talked about, that in a neutral atom, the protons are equal to the number of electrons. It doesn't mean that a neutral atom or a neutral object doesn't have any charges. It means that the number of positive charges are equal to the number of negative charges. Whereas in a positive ion or a positive object, that just means that the number of protons are greater than the number of electrons, or the number of positive charges are greater than the number of negative charges. And for that to happen, electrons had to be lost. Electrons had to be lost for an object to become positive. Remember, there are no protons transferring between objects or ions or atoms, right? So protons stay in the nucleus. Objects do not become positive by gaining protons, they become positive by losing electrons. And the negative ions become negative because they have greater number of electrons than protons, or there are more negative charges than there are positive. So we have a net negative charge because electrons had to be gained for that to happen. So that's that table very quickly. All right, we know about conductors and insulators as far as electricity is concerned. You know that things like metal and water conduct electricity very easily, and the reason they do that very easily is that if electricity is about transferring electrons, conductors do this very well because their electrons are not held very tightly. It allows the charge to move very freely, very easily. Things like copper, water, the copper in the wiring that we use in buildings, the outer electrons are very, very free to move, so electrical charge can travel very well through those materials. As opposed to an insulator, which has just the opposite effect, their outer electrons are not held very tightly, so charges do not move very easily through an insulator such as plastic, rubber, or wood. All right. So we've said this already, but I want to make sure it's clear that two neutral objects can be rubbed together, and they can become charged. It doesn't always happen, but it can happen if there's a difference in the electron affinity of those two objects. If one object wants to give up electrons and the other preferentially wants to gain electrons, then when they're rubbed together, those electrons can be preferentially transferred from one to another. Again, when that happens, we only transfer electrons, not protons, but the total charge of both objects remains the same. Charge is conserved. And what I mean by charge being conserved is this: if we have two objects that get rubbed together, and the total before the rubbing in the two objects, let's say they have 1,000 electrons total, right? They rub together and perhaps the electrons get preferentially transferred from one place to another. Okay, so this object lost electrons, it has become positively charged. This one gained electrons, it has acquired a negative charge. So they're no longer neutral. They're positive and negative. But if we count up the number of electrons again, remember that we didn't bring any electrons in and no electrons were transferred out, assuming that this is a perfect environment. So we still have 1,000 electrons. The amount of charge, the total amount of charge in these two objects remains the same. That's what we mean by saying that charge is conserved. We have the same number of electrons before as we do after. The only thing we did is really to separate the charge, and a good example of charge separation was the Van de Graaff generator that we used in class. The amount of electrons wasn't changed, it just that we transferred the electrons from the silver ball into the belt, so the ball became positive, the belt became negative. Charge was separated preferentially from one place to another. This can happen sometimes in a thundercloud. A lot of times you can get negative charges preferentially separating on the bottom, positives on the top, and that's what sometimes causes the within cloud lightning that we see in a storm. All right, we're going to skip these two parts, and we're going to go to look at electrostatic force and gravitational force. We already know about the gravitational force. We've talked about it before. We know that it is based on mass. We know that all objects with mass exert an attractive force toward each other. And remember that gravitational force, it's not one object pulling another toward it. Let me explain this to you a little more deeply. Remember that with you and the Earth, if this is the Earth and this is you, remember that there is a gravitational force from the Earth pulling down on you, but you have mass as well, so you are also pulling up on the Earth. So there are two forces going on, but it's really not two forces. It's the same force that really is bidirectional, because it's not that one object is pulling one towards it. It's two objects that exert a gravitational force on each other, and they are pulling each other towards each other. It's kind of like the slinky that I used in class, and if I have two equal masses on either end of this slinky, and you can imagine if I let it go, the slinky will meet right in the middle. They've pulled each other towards each other, right? It's not preferentially on one end or the other. But the reason why a lot of times we think that the Earth exerts a greater gravitational force is the Earth has more mass. And I illustrated that in class by using a larger mass on this side, for instance a baseball, and I had a small plastic ball on this side. And in this instance, the ball came together and it went all the way over toward the baseball. The greater mass had the least acceleration. But that doesn't mean the force was the same. We still had the same amount of force pulling both directions. It's just that that small amount of force caused a lesser acceleration on the greater mass because of our nice little F equals ma equation. Right? So the gravitational force is a force of attraction between two objects. They pull each other towards each other. A similar force to the gravitational force is called the electrostatic force. It exists between two charged objects. It has nothing to do with mass, and it also it could be repulsive, it could be attractive as well. So we know about these two forces, and I want you to think to yourself, ask yourself, see if you can answer this question. Which of these forces is stronger? See if you can reason through what you know about these two forces so far and see which one is stronger. The interesting thing is that most people think that the gravitational force is stronger. And that's for a lot of reasons. We experience gravitation every day. Many of us have gotten hurt by gravitation. Few of us, relatively few of us, have gotten hurt by the electrostatic force. But let's do a short experiment and see which one is stronger. All right, what I have here are some pie plates. Obviously, if I drop these, they will fall because of gravity, right? Because of the force of gravity. I set them on top of the Van de Graaff generator. They don't fall because there's another force that's pushing up called the normal force. And I know right now that the normal force must be equal to the gravitational force of these plates because they're not experiencing any acceleration. Remember, equal forces, they're in equilibrium. There's no acceleration. They're not moving. But if I apply a force to these plates that's greater than their force of gravity, they can lift up. And let's see what happens to these plates when I plug in the Van de Graaff generator. The plates easily lifted off the Van de Graaff generator. A relatively, kind of an exciting demonstration, kind of loud. But this proves the point to us that the electrostatic force is definitely stronger than the gravitational force, because the gravitational force is the force that's generated by the humongous mass of the entire Earth. That's the force between the plates and the Earth that causes the plates to fall. And in about 2 seconds, this very small Van de Graaff generator was able to generate a force greater than that force. And that proves to us pretty distinctly that the gravitational force is stronger. And you might wonder why, all right? And to answer that question, I'm going to go to the equation chart real quick and show you the value of the constants in the gravitational equation and the electrostatic equation. All right, so here's our formula chart, and let me get down here a little bit closer so you can see better, focus this thing out. We've used this constant before. This is the gravitational constant, 6.67 times 10 to the negative 11. And our new one is number 74, it's K, the electrical force constant, 9 times 10 to the 9th. Write these numbers down here. 6.67 times 10 to the negative 11th. I need to move up again. That's G. And K is 9 times 10 to the 9th. That's a massive difference, a huge difference. This one is much, much larger. There are 20 orders of magnitude difference between negative 11 all the way to positive 9. 20 orders of magnitude. That doesn't mean it's 20 times bigger. That means it's 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 zeros behind it. 10 to the 20th or 100 billion times stronger than the force of gravity. The constant tells us what is going on here. So the electrostatic force is definitely much, much stronger, and you probably know that if you've been hurt by electricity before. So it has to do with the constants. Again, there's G, there's K, 10 to the 20th times stronger. I'm going to skip electroscopes for now, and we're going to talk about the last thing that I want to discuss, and that is conduction and induction. There were three methods of heat transfer that we talked about. We talked about conduction, convection, and radiation, right? And there's two methods of charge transfer that I want you to consider. One is conduction and the other is induction. And I want you to go ahead and write these down on your notes, and then I want to talk about them specifically. Conduction is the transfer of charge by touching two objects together. That's simple to understand, and it's easy to remember because conduction with heat transfer was also the transfer of heat by touching two objects together. So that's the same concept. Induction is a new one, and it's charging an object without ever touching it. All you have to do is bring another charged object nearby. All right, let me explain this. Conduction. All right. When conduction happens, both objects will end up sharing the same amount of charge and the same kind. Let me explain why that is. If you remember when we talked about heat transfer, we considered that there were two objects, hot and cold. Perhaps this one is 100 degrees Celsius, this one might be 50 degrees. And if I touch them together, heat will flow preferentially from the hot to the cold object. And the temperature of the hot object will go down, the temperature of the cold object will go up. And I asked the question, when does heat stop flowing? And it's fairly obvious to see that heat doesn't flow when we no longer have hot or cold anymore. Heat quits flowing when they are the same temperature. So once they both reach a temperature of approximately 75 degrees, assuming they're the same mass, heat doesn't flow anymore. And it's the same concept with charge transfer by conduction, by touch. If we consider two objects, one has a charge of -10, let's say, that means it has an excess of 10 electrons, and perhaps this one is a neutral object. If I touch them together, it's not hard to see that electrons preferentially want to go toward the more positive object. This is not a positive object, but it's more positive than the -10. Electrons flow over here. Once this object has donated 5 electrons this way, this object has a -5 charge, and this object also has a -5 charge. At this point, there is no reason for electrons to flow anymore. Electrons do not flow any longer. We've effectively charged these two objects, and notice that we ended up with two objects that have the same charge. And that's the point with conduction. You end up with two objects that are either both positively charged, they're both neutral, or they're both negatively charged, and they also have the same amount of charge, the same number. So that's conduction. Induction, on the other hand, is a little bit different. Induction is more interesting. The neutral object, or two objects, end up becoming oppositely charged. That's the point with induction. If we imagine induction, you have two spheres here that are both neutrally charged. And next to sphere A, we bring a negatively charged object, an object that has a negative charge, but we don't touch them together. That negative charge causes the other negative charges in the previously neutral object to move over to the opposite side, because remember, negatives repel other negatives. So these negative charges get out of the way, but the positive charges want to move toward the negative charge because like charges are attracted to each other. So what we've done now is effectively polarized these two objects and made them more negative for B and more positive for A. Keep the charge there so that you maintain the electron distinguishment between positive and negative. Separate the two objects so that electrons can no longer flow, and what we have done is effectively charged these two objects without ever touching them with anything else. This one has acquired a negative charge, this one has acquired a positive charge. This is the definition of induction. Induction is the only way to get two objects that are oppositely charged. You cannot get that with conduction. And if at this point we now bring these back together and allow conduction to happen, they will again acquire the neutral charge that they had before. They will come back to the same charge because that's the result of conduction. So that's induction.